In the last video, we talked a little bit about different hybridization geometries with carbon atoms. The hybridization, depending upon whether it forms a single bond, a double, or a triple bond. Suppose that we have, say, two halogen molecules, where X can be any generic halogen. And if we just try to draw a simple Lewis dot diagram, we know that for the halogens, of course, their s orbitals are completely filled, and then the p orbitals, that can accommodate 6 electrons, they have 5 electrons in their p orbitals. So if two halogen atoms are going to form a molecule, then what happens is there's no hybridization involved. There is just simply a tip-to-tip overlap of the p orbitals from each atom, so that these two pair of electrons are shared equally between the two nuclei. For example, if this was an iodine molecule or a chlorine molecule, whatever. Now, suppose, let's consider very roughly the size of say an iodine atom compared to a chlorine atom. So here would be a nucleus of a positive charge for iodine, and then somewhere out here we have its most outer shell of electrons. And then for chlorine, that's going to be much smaller. So the attraction that the iodine nucleus has for its outer electrons is less than what chlorine would have for its outer electrons, for two reasons. These are further away from the nucleus, and then in the case of iodine, there are other electron layers in between that screen out that positive charge. So if iodine and chlorine form a molecule by overlapping their p orbitals, the electrons are going to be closer to chlorine, that has a stronger pull on them, the valence electrons that is, than what they'd be for iodine. So the chlorine has a certain amount of negative charge, and the iodine part has a corresponding partial positive charge. In other words, we say that the bond is polarized, and the polarization can indeed increase the strength of the bond. And we can try to get a handle on that situation just by considering a simple example. If we have, say, a hydrogen molecule, it takes about 17.1 times 10 to the minus 20 calories to break one of these bonds. Let's show it like this. Now, if we have a chlorine molecule, it takes about 8.55 times 10 to the minus 20 calories to break one of these bonds. Notice, first of all, the hydrogen bond is stronger than the chlorine bond, and again, the hydrogen atom is much smaller than the chlorine atom. But here, the bonds, or the electrons, the valence electrons, are equally shared, so we can say that each hydrogen atom contributes a bonding strength of about 8.55 times 10 to the minus 20 calories. And in here, each chlorine atom contributes about 4.75 times 10 to the minus 20 calories of strength to the molecular bond. So if we have, say, a molecule of hydrogen chloride, then we would think, well, a bonded hydrogen atom can contribute this much of chemical strength. The chlorine, each bonded chlorine atom can contribute this much. So if we have them together, if we add this, we would expect it would take about 13.30 times 10 to the minus 20 calories to break that bond. But if we measure it experimentally, it actually comes out to be 16.9 times 10 to the minus 20 calories to break that bond. And the reason, of course, the reason for that is the valence electrons are not shared equally between hydrogen and chlorine. So that has a slight negative charge. This has a slight positive charge. Opposite charges attract each other, and therefore it adds extra strength to the bond. So when we have polarized covalent bonds, indeed, we expect them to be stronger than when we have just a pure covalent bond. But that's not always the case. There can sometimes be other factors involved that can weaken the strength of a polarized bond. And let's take some simple examples to illustrate that point. If we have, as we discussed in the previous video, say an ethane molecule, a single sigma bond between these two carbon atoms, it takes about 83 kilocalories per mole to break this. So if we had a mole of ethane and wanted to break these single bonds, it would take about 83 kilocalories to do that. If we have ethylene, well, now we have the pi bond, and of course remember the pi bond results from lateral overlap with the p orbitals on each carbon atom, as we briefly discussed in the previous video. Then it takes about 146 kilocalories per mole. So we have a mole of ethylene. It would take 146 kilocalories to break that double bond. Notice that this strength here is less than twice the strength of the sigma bond. And again, the reason for it is when you have the lateral overlap of the p orbitals, that is not as effective overlap as when you have tip-to-tip overlap between sp2 orbitals, or an sp2 and an sp3 orbital. So the pi bond is a little bit weaker. But if we consider, say, the situation when carbon has a single bond to oxygen, like for example in ether, this would be much more polarized. Oxygen is much more electronegative than carbon is, so we'd expect this bond to be stronger than this pure covalent bond. But in fact, they're almost the same, 86 kilocalories, again, per mole. But notice that here, this bond is not much stronger than the pure covalent bond, even though this would be much more polarized. And to understand why, we have to consider now the oxygen atom. Here, when it has a single bond, like carbon, oxygen also is sp3 hybridized. Now, the orbital block diagram for oxygen. That's 2s, that's 2p. Looks like this. And now what happens is we do have sp3, all of these hybridized together to give 4 equivalent sp3 orbitals. When we say equivalent, we mean they all have the same energy level. So here we have single electron, and then we have these orbitals that have 2 electrons of opposite spin. We call these lone pair electrons. So for carbon, with the single bond to for oxygen with a single bond to a carbon atom, we have these sp3 lone pair electrons. And these double electrons then that are not participating in a covalent bond, they're repelling these negative charges, and therefore they have a weakening effect on the sigma bond here, so that even though this is more polarized, the bond strength is not much more than when we have just a purely covalent carbon-to-carbon bond. Now, let's say we have like a carbonyl group where there's a double bond. Notice here then, so now we're going to have a sigma bond and a pi bond, just as we had here between the 2 carbon atoms. Here, when we did that, the total bond strength was less than twice the strength of the sigma bond. Here, it is 179 kilocalories per mole. But notice the double bond here is more than twice the strength of the single bond here, 179 versus 86. Here it's slightly less. Does this mean then that when we have the overlapping p orbitals between a carbon and an oxygen, that somehow the overlap is more effective than if you have 2 carbon atoms? Most likely not. What is happening is that this oxygen atom is sp3 hybridized. This one is sp2 hybridized. Let's just show that. Let's say this, and this hybridized together. So we're taking 1 s orbital and 2 p orbitals to give us the sp2 hybridization. We combine 1, 2, 3 atomic orbitals. We get 3 molecular orbitals, sp2 hybridized, a single electron, and then these have lone electron pairs, and we also have left over 1 unhybridized p orbital electron. Well, what happens here in this bonding situation then, we have sp2 bond with the carbon, a leftover p electron that can form this pi bond, and we have these lone electron pairs again, 2 of them. Just like we did up here. But now this is sp2 hybridized geometry, These are now 120 degrees apart. Remember what an sp2 bond is, or sp2 orbital. They are 120 degrees apart from each other, this being an oxygen nucleus. Here, they're 109 degrees apart because we have the sp3 tetrahedron geometry, as we talked about in the previous video. So here, these lone electron pairs are spread further apart. Therefore, the destabilizing effect they have by repelling each other is reduced. So this sigma bond that's here is most likely stronger than this sigma bond here due to the relief from the more spreading out of these lone electron pairs. So we had a couple of things happen here then. We had a very polarized bond, but we saw that it's not much stronger than a purely covalent bond. And then when we form the double bond, the pi bond, and we change the hybridization of the oxygen, we have the spreading out of the lone electron pair that relieves that destabilizing effect, so that here then the sigma bond is stronger than what it would be here, and then overall we see an increase in bonding strength more than twice what you have here. Up here we didn't see that because up here we didn't have any lone electron pairs to contend with. So there's a simple example here then of how lone electron pairs and hybridization patterns can affect the bonding strength. And this video is getting a little bit long, so we're going to stop it here. Come back and join us in the next video. We'll consider a couple of other simple examples, and then that will set us up for the remaining videos for the next 20 or so. We can discuss different types of resonance systems.